from their homes, basically. This is the first edition of the Programmers Club in quarantine. I hope it's the last, but of course, I'm pessimistic. So, this talk is going to be a gentle introduction to the CUDA, or the Compute Unified Device Architecture. And it's named gentle. You'll see why in a few slides. Why? Because I'm not going to go immediately into CUDA. There's a good reason for that. So just to start, I think the obvious place to start is to just ask, of course, why do we even bother with parallel computing, right? So CUDA is something that it's a parallel programming API. You can think of it as like this. And the first question to ask is, why do we need parallel computing, right? So everyone has a specific problem, a script, some piece of code that in general takes a little too long to run. Maybe it will take you several hours, several days. And perhaps we would like to execute, to take this particular problem, split it into parts that can be executed at the same time. And in this way, we just take this problem that takes some time t, and we divide it by the number of parallel elements that we are executing, right? So for example, if I have a problem that takes time t, and I now execute it in 2 processor cores instead of just 1, ideally it would be twice as fast. Be aware that this can and is limited by the serial part of your code, correct? So if you have some code where 20% of it is serial and you only put the parallel part much faster, then, I mean, faster than, I mean, the serial part is still there. It's not going to go away, and this will limit your speed up. This is known as Amdahl's law, right? So now I've given the example of using 1 or 2 processor cores, but let's assume that we have a problem with a very large number of elements that can be processed independently. So let's say something like, I don't know, we have an array, a 3D array, and we want to apply a Laplacian stencil at all points of this array, right? So it doesn't matter in what order I start applying the stencil. I can apply it anywhere. Now, is there some architecture that would greatly benefit from having this large number of elements, or at least that can give me a large number of processors in a sense, or threads that can execute this stencil everywhere on the array? The answer is perhaps to start with a very silly analogy. So let's assume that we are all farmers and we are all trying to compete. We want to find the fastest way to plow a field. Now, what is the fastest way to plow a field? To use 4 very strong bulls, or to use an army of 50,000 chicken? And bear with me because this analogy will make sense in a bit. So the chickens individually are extremely weak. However, we have an extremely large number of them. The bulls individually are very strong, but we only have 4 of them. This is similar to how a GPU or a graphic processor works versus a traditional processor, a CPU, right? So on a CPU, probably in all of your laptops, you have, I don't know, 4 cores or something like this. So think of them as 4 very strong bulls. In reality, GPUs are not quite like that. So the GPU is built literally to be an army of chickens. So this is one example, the GTX 1080 or the Quadro P5000. In this case, this particular GPU is organized into a collection of something called streaming multiprocessors. Each of them has 128 CUDA cores. And just to differentiate between a CUDA core and the traditional processor core, these cores issue instructions on groups of 32 threads, right? So it's not like we are issuing instructions on only one thread. So if you start multiplying all these numbers, what you realize is that you have an extremely large number of chickens. The funny part is, if you are just going to execute things 1 instruction at a time, a GPU is painfully slow, so it will not work. Likewise, since you have such a very large number of threads, and the GPU in general tries to use this large number of threads to its advantage, for example, by overlapping which threads are accessing memory and which threads are doing computation, you really, really need a very large number of threads, people. So otherwise, it's just not going to work. For example, when I was talking to a friend of mine about some of the contents I would put on this talk, he asked me, okay, but one of the problems I'm having is I use MCMCs constantly. Can I use GPUs to accelerate MCMCs? And the answer is no. So the degree of parallelization of an MCMC depends on the number of walkers you have. And in general, that's just 32. So no, that's not enough. 32 threads is not enough to take advantage of the full GPU and to even do what I just said, which is to try and hide the latency of memory accesses with the latency of compute, correct? Bear in mind that the GPU also has another characteristic, which is you can think of it as a sort of a slave device that's connected to the host, right, to the processor. And so there's this bus which connects the GPU and the processor. And the most important part is that A, if you want to have something that's on your host side and you want to put it in GPU memory, first you need to transfer it, and this will take some time, so it's not non-negligible. And we will see later that there is a small amount of time connected to this. And two, it also means that the GPU on itself doesn't do anything, right? So you have to give it instructions, which, by the way, just goes into a real typical CUDA program, which is you have to queue specific functions to execute on the GPU, and you wait for them to come back to finish executing, right? So, okay. So again, so to just go back to what CUDA is, it stands for Compute Unified Device Architecture. It's a parallel computing platform and API that just allows you to use a graphics processor, which is something that normally we just use for graphical uses, like playing video games, for general purpose computing or scientific computing in this case. Bear in mind, it's not the only API that does this. So OpenCL is another example. However, I'm presenting CUDA, even though it's specific, can only be specifically used by NVIDIA GPUs, unless you use something to translate this into OpenCL code, basically. Um, uh, it's also the easiest one to use. So paradoxically, it's also the easiest one to use, to debug, and to optimize even. Um, it's not going to be very gentle when you actually see CUDA for the first time. And why? Because everything is written in C++ or Fortran functions called kernels. And these are queued for execution on the GPU by the host, right? So this queue of functions that are going to be executed is called a stream. You could have multiple streams. For the purpose of this presentation, I'm just going to use the default stream, which assumes that all functions that are executed are going to be executed in the order in which you queue them, right? So first in, first out, it's a queue. And second, I will not allow, so since we only have one stream, there are no overlaps between kernels executing in one stream and the other and so on. So it's simplified, okay? This will abstract a lot of the details of the underlying hardware, but admittedly, and from someone who works in this every single day, it's still not very easy, which got me thinking. So in general, almost everyone in CAUP, and I'm not sure if anybody from Lisbon is joining us, but also from school, and in general in most scientific environments, they don't write things in C or C++ immediately. So we try to write things in Python. And that's a very reasonable thing. First, because Python is a little bit easier. And second, because oftentimes, why do we have to reinvent the wheel when the wheel already exists, right? So many times we already have some package that already does quite a lot for us. Of course, this doesn't necessarily mean that I don't need to write CUDA from time to time, but many times there is no need to do it. Which brings us to CUPy or CUPy. So CUPy is a Python module, which I'm going to talk a little bit about today. That the basic idea of it is to think of it as a GPU accelerated NumPy. In fact, you can even think of it as a drop-in replacement for NumPy many times. And it allows you to do many of the things that you already do in NumPy. So matrix operations, FFTs. FFTs is the example I'm going to discuss here today. And you can use it as well to write explicit CUDA. When you do use it to write explicit CUDA, it has a tendency to sort of sweep under the rug a lot of the C or C++ code on the host side, Remember that the kernels are still in C, C++, so that I cannot avoid. Note that it's not the only Python module that enables that has support for GPUs. For example, Numba allows you to use GPUs as well in a completely different way. And often you have some modules or libraries that they already use GPUs for doing their own thing, like TensorFlow or Keras, etc. So a few of the deep learning stalwarts. Okay, so before I go into the example of CUPy, I think it's neat to leave some 2 slides on how to install CUDA, CUPy, CUDNN, which are basically all the dependencies you need for CUPy. If you are using Linux, so I cannot tell you anything about Windows because I don't use Windows for this. Mac OS decided to stop supporting NVIDIA graphics cards, so we cannot use them. But if you use Linux, you're in for a hell of a time because this can be a bit time consuming and it can be extremely frustrating. And why? Because you need to have the correct version of the CUDA, of CUDA itself, of the graphics card driver, and of the Linux kernel. And then of CUDNNs, and of course CUPy. So this, admittedly, it's possible that you will find installing CUDA more difficult than just using the examples I'm going to show next. Either way, even though I'm not going to do this live, I think it's important to at least leave some pointers on how to do it. So overall, in terms of making sure that you have, first just write down the CUDA version you want to install, 10.0, 10.1, 10.2, whatever. So 10.2, I think, is the most up-to-date one. 10.0, which is the example here, is what I have installed on my computer. And the graphics card drivers it requires. So for this specific example, I noted when I was installing CUDA 10 that the driver 440, which is the long-term version of the driver, so it's always 4 something and not 3 something, was compatible indeed with kernel 5.5. So of course I had to install kernel 5.5. This depends on your distro, on the Linux distribution you are using. Most of the times you will have a repository for updating the kernel. When you do have the correct kernel, cool. It means that you now start installing the driver and you can start installing CUDA. I generally install them manually and not from the repositories. In Ubuntu, I think it's fine to install from repositories. In CentOS, which is the Linux distribution I'm using, I haven't had much luck. So I prefer to just get the run files directly from these 2 web pages here, okay? After you install them, so after everything is installed, you need to test if it's working correctly. So the first thing, don't get scared if you don't see a graphical user interface. This can happen. First, you need to understand if the driver is indeed installed and if it is working. So if you just go with NVIDIA SMI, so this command here, NVIDIA-SMI, then you will get some output. So again, I can show it. So just like this, saying what is the graphics card driver version. For some reason, it's telling 10.2, even though it's not 10.2, it's 10. And I can actually show that. And then it just shows which graphics cards you have installed and some stuff about it, right? So with what memory they are using, temperature, and so on. But in principle, if this spits something out, it means that the graphics card driver is fine. It installed correctly, okay? So I also mentioned that you can test this, you should test this even if you don't have any graphical user interface, because oftentimes not having a graphical user interface doesn't necessarily mean that the driver itself is not well installed. For example, you noticed when I use the NVIDIA SMI command that I have multiple GPUs. And one thing that can be incredibly irritating when installing this graphics card driver is that it replaces the Zorg configuration, so X11, default configuration, right? So, and what happens is that it doesn't actually know what is the default GPU to send this graphical output, right? So even though I actually had, this happened many times, by the way, even though I had the HDMI cable connected to a specific GPU, it wouldn't output the guy on that one, correct? So, okay, this just means you have to look at the output, for example, in this particular log file, see the complaints, like Is this a valid device, what you are trying to use to start your graphical user interface? Is it, I don't know, do you have a compatible a monitor attached to it, etc.? It will complain. And then, of course, you just have to go to X11's org and correct that. Okay, so this is already a bit scary. So slide number 2 at least is a bit easier. So CUDNN is straightforward. You just have to use the script from here. And then I think you have everything you need to use a CUPy properly, okay? So assuming all of this was properly installed, you can do two things. You can try to build CUPy from source, which is a bit tricky because it requires an extra library, or you can just install it from a precompiled wheel. From the precompiled wheel, the only thing you need to make sure is that this digit here, 100, matches the CUDA version you are using. Okay, so for example, if you have 10.0, you put 100, 10.2, you put 102, so on. Okay, so that's it. Now, finally, let's get to an actual demo and see CUPy in action. So it's true that I tried to adapt to the audience, and I want to show CUPy in action by using something with which normally can be done with NumPy, and I will try to change it with CUPy. But at the same time, it's also true that I am in an area which is cosmology, and not many people are doing cosmology here, right? At least in CAUP. So most of the people are doing exoplanets, or they're doing stars, or whatever. And I don't know anything about it, correct? It's difficult to find for me an example which I can just translate into that. So I will just go with, okay, maybe I can find something in cosmology that at least showcases the power of CUPy and at least shows that it can be useful. The example I'm going to take here today is to generate a Gaussian random field. Now, a Gaussian random field is something that you use normally in simulations in cosmology to try and have some initial conditions that obey a specific power spectrum. And the way you do this is you just start with assuming that you have some sort of noise in k-space. So some sort of, in here, this is generated using this random normal from NumPy. And this noise must have an amplitude which is given by the power spectra. The power spectra itself, which just depends on, the magnitude of whatever point in k-space you are. And then you just do an inverse transform. So this is not exactly a complicated thing to do. So let's just run this particular example and see how long it took to run for an 8,192 squared array. So you see that just to create the k-space, it's 1.4 seconds. To create the amplitude, 3.47. For complex random noise, it's even more time. And then we're going to do the inverse fast Fourier transform, which is 5.84. Sorry, so it's 7 seconds. And overall, this takes 17 seconds. Okay.
Can you zoom in a bit?
Yes,
The
sorry
page.
about that.
Thanks.
So hold on. No, that's not it. Wrong shortcut. No. Yeah, it's just I have the keyboard with the blank keycaps.
Excellent.
Right? Okay, can you see better now? I can
Very well, very well.
perhaps
Yeah, thanks.
I can highlight again the stuff I mentioned. So, for example, this is the amplitude here, like I said. So you have some sort of power law. So this is inverse of the magnitude of k to the power of something. It doesn't matter what alpha is. In this case, I think I just use it at 3. Fine. And you're going to multiply this by some normal noise, correct? And then you just do an inverse transform. And that's it, right? And then you have your Gaussian random field. Okay, so you can see here the Gaussian random field. So the time taken to generate for each part, I'm going to time explicitly each part on purpose because I want to show what happens when you just put CUPy and how much faster it gets, and what happens when you don't, right? So there's an interesting point to make there. So the time to create the in general, it's not like this takes a long time, so 17 seconds is not a lot, but it's also not necessarily a very large array. You could have something a lot larger. In fact, in our type of simulations, we generically do not use 2D arrays, we use 3D arrays. And the moment you multiply this by 8,192, you're going to have a bad time because it's huge. So, okay, how do I do that with CUPy? I am going to keep exactly the same amount of time to generate the K space, so the K array. I am not going to use CUPy for that, but I am going to do something a bit different. I'm going to generate it anyway on the host, and I will use CUPy as array to convert this output into an array that exists on the GPU. So basically what I'm trying to do is I'm transferring over that bus I mentioned, so over the PCIe bus, to get something that was on the CPU side onto the GPU. In order to ensure that this transfer has already finished, remember, executing kernels. In this case, it's not a kernel, it's just executing a transfer, so from one side to the other, is something that on one hand goes on the stream, and second, just because it's on the stream to be executed by the GPU, it need not mean that after it was put in the queue, the processor cannot continue doing something else. So it's important to put something like this to synchronize, or to at least say, okay, everything that executed on this, that I sent to execute on the stream must finish on the GPU before the processor side can continue doing anything else, right? So this is already going to tell us two things. First of all, given that I'm generating exactly the same K space, it shouldn't take too much of a difference compared to the previous time. And second, if we see a large difference, it means that we are wasting too much time transferring things from the host side into the device, so into the GPU, right? And second, it also means that this time here indeed corresponds to when we finish transferring everything. So it's not like the transfer is still going and I already stopped the timer. That does not happen, okay? From this point on, I will try to use everything with CUPy, okay? So I will do the CUPy power. Again, as you see, this is exactly just replacing NumPy with CUPy. It's not like there's a huge difference. For generating the random noise, again, CUPy. For the FFT, the inverse FFT, again, just drop in CUPy. Notice that for simple operations like multiplying two CUPy arrays or even just dividing by a constant or whatever, CUPy also supports this behavior and will do it for you, right? So for example, when we do here noise times amplitude, there is no need to convert this back into a NumPy array and then again into a CUPy array. In fact, if that was the case, we would get an error because you cannot, right? So what happens is CUPy inverse FFT expects a CUPy array. So if you give him a NumPy array, he will complain. So, okay, we've seen all of this. What is the amount of time to generate this stuff? So as you can see, to create the K array, it took us actually more time than in the normal example, but for a good reason. It's not that it took us more time, it's just there's some time involved in taking things from the CPU into the GPU. Notice as well that everything else is a lot faster. So instead of 17 seconds, we only take now 2.5 seconds overall. So indeed, there is a huge speed up, but again, Amdahl's law, I'm limited by the serial portion. The serial portion is going to be not only the time to the generation of the K-space array, but also to transfer things into the GPU, correct? So I hope that this example was at least useful. At the end of the day, I think that what this shows is that even without going immediately into CUDA code, you can start using GPUs in your own projects just by using CUPy as a drop-in replacement. So now this leads me to the second part of the talk, which is the ungentle part, which is where we actually get into the meat and bones of CUDA. So in order for me to explain how CUDA works, see?
Sorry, yes? Quick question. Which GPU are you did you run this on?
Okay, so I am running on the 1080 Ti that's available on this desktop.
So is that a lower-end, high-end GPU? Or?
This is a high-end GPU, yes.
Okay.
So
you would expect much worse results from a worse GPU, or things would scale more or less the same?
Okay, that is a good question. And it depends a little bit on the problem and depends on the GPU. So, for example, let's say you have something like a GTU 1030. So this is from the same generation as this 1080 Ti, but it has a very different type of memory. So this VRAM you see here, it basically is the same as I think normal RAM memory. So it has a really low bandwidth. I expect that in any problem where memory bandwidth is the bottleneck, you will see much worse results on the 1030. Okay. Um, I understand that to some point it might not seem too good of a result, the fact that we only got 2 seconds. And of course, you're probably wondering, okay, we don't have a high-end GPU, we have a weaker one, we want to obtain better results. But like I said, don't despair. This depends on the GPU you have. It depends on the problem.
No,
And
I think these results were very impressive. I was just wondering if you would get not as good with a, let's say, more normal GPU. It'll
okay.
probably not be as good, but it'll still be a bit better than the serial version.
In principle, yes.
Okay.
But again,
Okay.
this will vary a lot from GPU to GPU. And there are some small, subtle things that, okay, CUPI doesn't expose. Well, for obvious reasons, it cannot expose because it's supposed to be a simple and easy way to use CUDA, right? So you're not going to expose things about how, for example, what I'm going to talk about next, about the size of each particular memory block that you use, or the size of how you group threads, etc. So these optimizations are not performed. And the reality is sometimes something very subtle like this can hinder your performance significantly. Okay, so the goal of this talk is not actually to go into performance optimization. In fact, just because of using a Jupyter notebook, it's already a bit, I don't even know how to do it. Because in general, if you want to do performance optimization, you run things either in pure Python or in pure in C, sorry, Python plus C++ or C++ immediately. You have some executable and you pass it to NVProf, for example. And then this instruments your code and tells you where the bottlenecks are. But this, I mean, it's going a little too much. I think in general, you can still expect to obtain a reasonable speed up for most of the GPUs you have. So even in the case of the 1030, I still think you will obtain better than the serial case.
Okay, thank you.
Okay. So, sorry about, where was I? Okay, so to get in the true meat and bones of CUDA, I think I can give a little bit more about how the abstraction from the hardware itself is performed. So in reality, when I'm writing CUDA code, it's not like I'm thinking, okay, now I need to put these threads executing in this particular streaming multiprocessor doing this particular thing while these threads do that thing and whatever. That's not how it works. As you can imagine, that's too much. It's too much of a hassle. It's too difficult. And honestly, if that was the case, then it would rather be better to just write in assembly and that's it. In reality, what happens is that you're going to do something a little bit different. You're just going to assume that you create a grid of thread blocks, right? You can give the dimensions you want to this grid. It can be 1D, 2D, 3D, whatever. You're going to put a specific number of threads in each block. And the only thing that you know is that in general, these blocks, you can have multiple of them executing in a streaming multiprocessor. And that is it. Okay, so the size of the thread block and how you divide your threads for the specific work problem is what guarantees you good or bad performance. But again, don't think about this too much. What I wanted to also highlight is that the way we organize threads and the different types of memories that we can find in a GPU are actually related. For example, if we have something in global memory, so this is this memory I was speaking about of the 1030, right? So which has the VRAM, the video RAM. For in these cards, it's 16 gigabytes total. And I mean, you can create a large array there that fills those 16 gigabytes, no problem, and you can do some operations there. All threads can see the memory in this global memory array. But what happens if I need something a bit faster? So let's say I have some sort of a smaller memory per streaming multiprocessor. This memory in terms of bandwidth is going to support something which is in orders of terabytes per second. It is much smaller in total than the full VRAM, but the scope of the memory itself is also not all threads. So in other words, if I have a small block of shared memory, this is only accessible by the thread block I'm talking about, a specific thread block, so not the entire grid, right? Then we also have an even faster amount of memory, which is a bit smaller, called local memory or register memory, if we want to call it like this, which is basically the same thing as saying we have private memory for only that thread, right? So this is a value that only that thread has. Okay, so just to give a little bit of a glimpse into, it's not necessary to perhaps go full on into all the examples about shared memory and so on, but I think I can at least give you an idea of how things are organized in terms of blocks and grids and how you would obtain it, right? So in terms of the thread hierarchy you would find, so let's say you just have a 1D grid. Essentially, you will just number your blocks. You have blocks along the X direction, and you say that each block has, I don't know, a size of 8. In this particular case, it just means that thread ID x.x is just going to return you the ID of the thread inside the block. So if you want to obtain the ID of the thread over the entire, over all the threads, right? So a global thread ID, you must use the block ID and the thread ID, not just the thread ID, correct? So again, I can demonstrate this with the raw kernels. So I think the easiest way is to perhaps start in the classic hello world. So in CUPy, we can create CUDA functions basically that look like this by using the raw kernel. So don't worry too much about what you're seeing on the header about this extern C. So just remember that each function you create in C for CUPy must have this decorator underscore underscore global to indicate that it is a kernel, correct? You have to put again the arguments of this particular function. Then you can do stuff inside, and this is just one string that you pass to CUPy raw kernel. The name of the function in C must be the name of the function you put here, so CUPy knows what to compile, right? So it's going to take this particular function and it will compile it into GPU code, correct? And now you can start using it. So this is a very simple example. Why am I'm in the wrong example? Sorry, guys. It was supposed to be hello world first. It's a very simple example, which literally just has no arguments whatsoever, so it's void. Then I'm going to ask, okay, so what is the thread ID, the global thread ID? As you can see, you must use the block dimension, the block ID, and the thread ID inside the block in order to get the global one. And then I'm going to do a hello world. Okay, so weirdly enough, when I run this, nothing comes out here on Jupyter. But if I go to the terminal, you actually see the output. So, okay, whatever. I don't necessarily care too much where the output is coming. The only thing that matters is just showing you that, yes, you can get a hello world from thread IDX and block IDX, and it gives you the correct coordinates for each particular thread, right? So if you wanted, you could even put the TID of each thread here in front. And, you know, you have your hello world. So that's more or less how it works. One thing that is important to mention about CUDA, do not expect to put all the functions from C or C++ inside the kernel and have them be immediately supported. That will generally not be the case. I can demonstrate that actually. So we used printf to get some sort of output to get the hello world. Let's say we put std count. Boom. So immediately he cannot even compile this particular kernel and he doesn't understand what it is, right? So CUDA does not know the std library, for example, right? So again, this works okay, the other one does not. So be careful about this. Okay, in terms of what is going on, we just have a grid size of 5, so we're going to put 5 blocks, and inside each block we just have 5 threads. So very simple. Another small comment that we can make here. So I mentioned before that the way you organize threads can impact performance. So this is a bit complicated and will depend on the problem size, the architecture, so the specific GPU you are considering, and inside the same architecture, just things like having slightly different memory can cause differences. But overall, the pro tip I could give, or the really cool tip I can give here is remember the magic number 32. So instructions in CUDA are issued in warps of 32 threads. So if you can ensure that your block is some multiple of 32, you are at least on the right path to have some good performance. It could even be 16, by the way. So just integer or a half integer, it's fine, right? So something that just not 5, for example, as in this example, which is a bit funny to say. Yes, putting something that you shouldn't do in an example. How educational. Okay, so to the more interesting example, but still kind of unnecessary, because let's be honest, if you want to just add to arrays, you can still just use normal CUPy, so you don't actually have to write raw CUDA. But anyway, it's a bit more involved. This shows how you can put a little bit more arguments inside and then how the sum actually works. So it's very simple. So you just have the thread ID, the global thread ID, and you will say that for each array at a specific index, you want each thread to just sum the elements of the array at its specific position, correct? So it's just that. This particular guard you see here, this is just standard good practice. So in general, you don't want, if you declared the grid and the block size correctly, you will not have more threads or threads that try to access indices of an array that do not exist because the array is too short. But overall, it's not a bad idea to put this. So the example itself works in more or less the same way, except now instead of just doing grid block as usual, you actually have to give a few more arguments. Bear in mind that given that we are trying to get Python CUPy arrays basically into CRC++, there is a sort of a conversion between the two. So it's not like this will always work, right? CUPy will not perform early validation of the arguments passed to kernel. So if you just pass a string into it and he expects an integer, he doesn't care. He just runs anyway, but you will obtain garbage output. Be aware as well that some types, for example, map into specific other types. For example, an array which has a D type where each element is of CUPy float 32 maps to a float pointer, correct? So to an array basically declared on the heap, so dynamic memory. If you have, I don't know, U in 64, then you can go for long, so for integers. For anything that's not an array, so let's say you just wanted to pass, in the example above, you just want to pass the number of threads that you will have, or the number of elements, you just pass 25, correct? You can also do that, right? So you just have to be aware that an integer in one side maps to a long in the C side, double, float here, bool to bool is the easiest one. And you can also use complex types. So you would be forgiven for thinking that just including the cu complex.h header, which is the normal one, if you want to actually write complex numbers in CUDA, would work. So just putting this header inside this kernel, inside, no, so here, basically. But in reality, don't do that. So I'm not exactly certain why, but the correct way to do it is to use CUPy/complex H. So I think it's just something that's related to CUPy. In general, it could be that the complex float value we have here is also not binary compatible with typical CU complex. So you cannot even do, for example, for the C++ inclined people here, it's not like you can just cast from one thing to the other, right? Okay, so this was it for the two simple examples. I don't know if people have some questions for now. No? Okay, if not, we can go into the slightly more complicated example. Now, don't worry too much about this one. It's also something that I saw at least 2 years ago, so it means that I also have some questions about how it works. But the main point of this is how probably doing the transpose of a matrix looks like inside CUPy. So CUPy will try to be simplified, of course, but it also needs to try and be a little bit optimized, correct? And how do you optimize this stuff? Well, you try to use the memory hierarchy I told you about before. So shared memory is much faster. And if you have some sort of memory access which is going to be inefficient in global memory, a good way is to just transfer whatever you need to use into shared memory and then do whatever operation. In this case, the operation is just to do a transpose, correct? So this way this works is very simple. So you just create a tile of shared memory. Remember, you must have this underscore underscore shared underscore underscore to indicate that. The size of shared memory must be known before, so explicitly on the kernel itself. So it's something that when it's compiled, it's known. So you cannot just pass here as an argument. Sorry about that. It doesn't work. And then what the example does is it finds the coordinates of the matrix in the original matrix in global memory, which is given by ix and iy. It gives you a linear index because in general, all memory that you find in CUDA is linear. So for example, if you have a 2D array and you want to access it, you must use something like this. So ix plus iy times the side. It's a bit irritating, I know, but I mean, with either a proper define or some macro, something like this, you can circumvent this easily. So for larger projects, this is not a nuisance. So now comes the part where I have a little bit of trouble understanding, which is what if we want to see the thread index in the transposed matrix? And this is a bit funny because the way to do it is that you're going to try and swap x and y, but you're going to try and swap x and y inside the thread block as well. So first you need to find the thread index in the transposed block, which is this bidx, and you will try to use this to find the row and column. And then, of course, just finding it inside the block is not enough. You need to find again the transposed column and row in the global thread index, correct? So this gives you the TO index. Notice that here we have NY, we have IY and YX. And notice as well the fact that for this particular BIDX index, we're not using only block, say the X part of block dim and thread IDX and thread IDX itself. So we are doing a bit of a mixture. What happens afterwards is that now we can start to basically read from the input array with the global original index. We read into shared memory just using this thread IDX, again, local thread index, right? We issue an instruction called sync threads. Sync threads is important when you are reading or writing to shared memory because you want to make sure that when you start reading again or writing or whatever, the previous operation finished. So for example, if I did not put sync threads here, what would happen is that when I try to transpose, so again, taking from the shared memory tile back into global memory, what would happen is that it's possible that we would start reading from shared memory in this line here, while this previous line hadn't even finished. So as you might imagine, that will first not give the correct result, and funny enough, it wouldn't even give the same result if you execute the kernel twice. So that's it. This one is a bit more involved in the sense that we will use a 2D grid size and a 2D block size. Overall, it's easy to show that the result is correct. So again, and I guess that's more or less it. So just to conclude a little bit, CUPI was introduced as a gentle way to introduce CUDA. It removes a lot of the complexity, as you saw. So even this relatively simple examples can be complicated even for myself. So I never enjoyed reading the matrix transpose. I'm going to be honest, but this is good because any example that's a bit complicated, and in this case, it's complicated and it's present in this particular book, CUDA Professional Programming. And if you walk your way to the example itself, it gives you an even better understanding of shared memory and etc. The shared memory of thread blocks, etc. So it's basically one chapter that if you do it once and you understand, you will learn a lot about CUDA. At the end of the day, there's more stuff that can be used to learn how to use CUDA. So I'm a big fan of the GPU Technology Conference this year. So normally the GPU Technology Conference is paid, and you have to pay a lot to get there. So it's usually in the US. Of course, just getting to the United States is an issue. This year, because of the present coronavirus situation, it's all digital, so you can just access most of the lectures. The only thing that was paid, and it's all free, right? So the only thing that was paid is hands-on expert help, right? So if you needed someone to literally, so you just give them the code and say, I have this problem, can you help me? Then yes, of course, that's paid. Some more very cool resources. So the CUDA Pro Tip blog is extremely useful. It has a lot of small tips in terms of performance. And when you install CUDA itself, don't overlook the option to install the CUDA samples, right? So there's a cavalcade of examples, small examples that cover very, very different parts of CUDA that allow you to do, that are a very good start for many of the problems we might have. So that's it. Thank you. The overall conclusion is it's nice to harness the power of chickens. And I hope that this Programmers Club was useful in some way. I tried to make it useful when I presented CUPI. I hope it was. Okay? So that's it on my side. When but do you mean mhm, mhm. Okay, so first of all, you would not do it for a very small problem size. So that's the first thing you need to keep in mind, as I mentioned. The second is um, it depends as well on the libraries you have and how easily you can implement things. For example, if there was no library to do FFTs, I would never even dream of doing FFTs with GPUs, correct? So, okay, the FFTs was perhaps a bad example because they've been around for a little while, but actually, they are a good and a bad example. They are a bad example in the sense that yes, we've been able to use FFTs with GPUs for a long time. But for example, consider my use case. I have a particular domain that's distributed amongst several processors, so amongst multiple GPUs, and I want to do an FFT over them. And the reality is doing multi-GPU FFTs is not a very easy thing. So, and it's actually not very well optimized overall. So this is already a case where one could consider not going into GPUs, correct? So, right? So again, there's a bit of a straight trade-off. You might have a problem that's much larger than the GPU, and therefore you have to sort of hot swap parts of it in and out of GPU memory to do the FFT. Or you decide to do this over multiple GPUs, and you see at what point is it this thing not scaling properly, right? So, or not performing well at all. It's not something I can easily say the entire time, like go immediately for GPUs, everything is faster, they are the silver bullet. They are not, and I think that's the other conclusion of this talk. So the chickens are very useful, but they're chickens. So They are useful only in a small subset of problems, and they will not be useful for everything. For machine learning, they are extremely useful as well. So again, for everything that uses TensorFlow, Keras, etc., I mean, don't ask me because it's not like I have a lot of deep learning experience. But this year's GTC was extremely centered around this stuff. Overall, like I said, it depends on the problem size and depends a little bit on how slow it already is on a traditional processor. Okay. Thank you. Okay. Thank you.
Thank you very much. Thank you.